Hi, and welcome back to the 6th lecture in this master's level introductory course about galaxies. This is also the 3rd and last lecture in our little mini-series about star-forming galaxies. And as I have made a little bit of a habit of by now, this one is also split up in 3 parts, each of which is going to come in its own separate video. The first part, this one, is going to be about scaling relations. The second part is going to be about starburst galaxies, and the last part is going to be about chemical evolution in star-forming galaxies. But jumping straight right into it, what are scaling relations? Scaling relations are empirical relations which have in common that they describe how certain quantities scale with each other. The typical mathematical form of a scaling relation is, as we see here, that the logarithm of quantity A equals constant B plus a coefficient C times the logarithm of quantity D. This basically means that in a sense, these are what you can call linear in log space, or they are linear relations between logarithmic quantities. One of these, the first one we are going to take a look at now, is the so-called Tully-Fisher relation. This is an empirical relation between the luminosity and the rotational velocity of a disk galaxy. We see that the logarithm of the luminosity in units of 10 to the 10 solar luminosities equals the constant B plus the coefficient beta times the logarithm of the maximum rotational velocity in the galaxy in units of 200 kilometers per second. These can seem a little bit arbitrary, but again, this is because these are empirical laws that have been fit to the data simply and then expressed in a way such that they are as simple as possible to work with in our everyday computations. The constant B has been found empirically to be around 0.5, and the same is the case for the coefficient beta. Vmax, the maximum velocity of rotation, is a distance-independent measure, which means that the Tully-Fisher relation can be used for measuring distances to galaxies, which makes it incredibly useful. Because if we take a look at it, we can see that if we can measure the maximum rotation velocity of the galaxy, then we know its luminosity, which is an absolute quantity about this galaxy. And then we can take the luminosity and we can compare it to the apparent magnitude. Well, the luminosity can be converted to an absolute magnitude. We can compare that to the apparent magnitude and use the distance modulus to compare these two and find the distance to the galaxy. And again, that makes this very, very useful for if we want to build an understanding of cosmology in the nearby universe. However, we cannot use the Tully-Fisher relation for precision cosmology or for any kind of cosmology at high redshift. A more modern version of the Tully-Fisher relation is the so-called baryonic Tully-Fisher relation, which is the same relation but with baryonic mass substituted for luminosity. And this should not really come as a surprise that this also works, because all else being equal, a larger baryonic mass means a larger number of stars, and a larger number of stars means an equally or correspondingly larger luminosity. Another important such scaling relation is the Mass-Metallicity relation, which states that the logarithm of the metallicity in terms of solar metallicity is given by the constant minus 0.1 plus the coefficient 0.35 times the logarithm of the stellar mass of a galaxy in units of 10 to the 10 solar masses. This relation flattens out, you can see, at high masses. If we zoom in here, we can see it, but it's perhaps especially clear if we look at this zoom in over here. that from around 10 to the 10 solar masses, a little bit above and upwards, this one becomes flat, so we can no longer use that to say much about the metallicity of the galaxy, except that it's going to be larger than a certain value here. The mass-metallicity relation can be explained by a combination of chemical evolution inside the galaxy, which is something that we're going to look at later in today's lecture, and in and outflows. So inflows means the infalling gas from the surrounding environment, which often, but not always, is pristine gas from the IgM that falls into the galaxy, gas that has never been part of star formation before and therefore contains almost no element heavier than helium. So of course this gas, as we talked about, as we're going to see later, will mean that the metallicity will go a little bit down. We can also see that, on the other hand, strong star formation provides what we call feedback. That means that the stellar winds from young stars, and in particular from supernova explosions, can push and accelerate a lot of this gas. And if the star formation or the supernova explosions are strong enough, it can actually accelerate it to escape velocity and push it out of the galaxy entirely. So these different effects together can explain the mass-metallicity relation. Finally, we also have the star-forming main sequence. This is a broad sequence where most star-forming galaxies fall in a diagram where we plot the star formation rate versus the stellar mass of a galaxy. As you can see, a best fit value is that the logarithm of the star formation rate in units of solar masses per year equals constant y, which is around 1, plus the coefficient kappa, which is about 0.8, times the logarithm of the stellar mass of the galaxy in units of 10 to the 11 solar masses this time. I remind you that the last relation involved the stellar mass in units of 10 to the 10 solar masses. Again, this is because these are empirical relations, so that's basically what comes out of them. We can also see that this is a broad relation, especially because this is in a double logarithmic coordinate system. So the band around here actually corresponds to quite a strong variation in this correlation, or quite a strong scatter in this correlation, but it's still certainly there. We can see sometimes that episodic star formation can give rise to what we call the star formation main sequence staircase, which we see illustrated here. What happens here, of course, is that if we have a strongly episodic star formation, that means that we have a short and quick burst, an uptick in star formation rate, so it goes up very suddenly. And then as it is higher, it produces stars at a similar star formation rate, and that means that the stellar mass of the galaxy goes upwards, of course, until it kind of dies down, and then it can get another uptick and so on, and move upwards in this along this sequence. We don't see early type galaxies in this plot or in this diagram because the early type galaxies have a very, very low star formation rate. There are also galaxies that fall in between these two populations, you can say, galaxy types. As you can say, there is a little bit like when we had the color magnitude diagram, right? Where we had the red sequence and the blue cloud and the green valley. Now we have something a little bit similar here, where we see that these galaxies are forming or are falling in between, which is probably a transition phase. These are probably galaxies that are almost but not completely out of neutral gas yet, and therefore are on their way to kind of fall down into the red sequence of early type galaxies with no star formation in them at all. That was all for this first part. Thank you for staying with me this far, and I will see you in the next one.